Hi there, welcome to this engineering mechanics video tutorial. My name's Terry Brown and I'm a lecturer and mechanical engineer. Today we're going to look at drawing shear and bending moment diagrams for a loaded beam. So you can see the example problem that we're going to look at today. So we have a beam with a uniformly distributed load and it's supported by a pin support at A and a roller support at B, and we're asked to draw the shear and moment diagrams for this overhanging beam. So the first step in the solution is to draw the free body diagram of the beam and then apply our equations of equilibrium to determine the reaction forces at each of the supports. So we draw the beam free of its supports and label the important points. Next we will add the load. So we have a uniformly distributed load all the way across the beam with a magnitude of 8 kilonewtons per metre. So now we can start to add in our unknown reactions. So at end A here we have a roller support, pin support, So we'll have force in the vertical direction and a force in the horizontal direction. And we'll label those RAX and RAY. Then at B we have roller support, so we have only a vertical reaction at point B, and we'll label that RBY. Let's put on some dimensions for reference on our free body diagram. Now that we have our free body diagram, we can start to apply our equations of equilibrium. So we'll start with sum of the forces in the x direction equals 0. In this case we have no horizontal loads applied, so our reaction force here, RAX, in this case will be 0. So we have two unknowns left, RAY and RBY. To find out one of those straight away, we'll take moments. So let's take moments about point A. So some of the moments about point A, taking anti-clockwise as positive, equal to 0. So we'll have the moment effect of RBY and the moment effect of the distributed load. For the distributed load, we're going to use the equivalent single point load. So the equivalent single point load for this distributed load will be the distributed load, 8 kilonewtons per metre, times the length over which it acts. So the equivalent single point load here will be W times L. And we of course also need to know where that acts. And it acts through the centroid of this distributed load, which in this case, because it's uniformly distributed, will be halfway along the length of that distributed load, so L over 2. So now we can start to write our equation of equilibrium for sum of the moments. So we have our distributed load in its equivalent single load here, so W times L. So I'll have 8 times 6, and I put the minus sign here because we're taking moments about point A, so this force will be tending to rotate around clockwise around point A, so therefore that's a negative moment according to our sign convention. Okay, so that's the load. We now need to put in the distance from point A, so that will be L over 2, so that will be 6 over 2. Okay, so the total length here is 6, so that location is 6 on 2. And then we have the reaction force RBY times its perpendicular distance, which is 4. We have no other loads causing moments about point A, so we can put all equal to 0 and rearrange that to solve for our reaction force at B. RBY equals 36 kilonewtons. So we have one unknown left, our reaction force RAY. So we'll use sum of the forces in the vertical direction equals 0. So we have RAY minus the distributed load, so 8 times 6 for our equivalent point load, plus RBY, all equal to 0. And because we've already calculated RBY here, we have one unknown, so we can solve for RAY, which gives us 12 kilonewtons. Having now determined our reactions, we can go on and determine the internal shear and bending moment equations for the beam. To do that, we take an imaginary cut through each section of the beam and then determine our internal shear and bending moment as a function of the position in the beam. So let's start by taking a cut through section AB. So when we do that, we take our cut, so here, and then we look at either one side or the other of this imaginary cut that we've taken through the section of the beam. So here we've taken a cut somewhere through the beam, partway between points A and B. And in this case we're going to look at the left-hand side. So we've just drawn the left-hand side of the beam here, and then we can start adding in the loads that are applied to that left-hand side of the beam. So we'll have our reaction force that we calculated previously, and we have our uniformly distributed load that acts over this portion of the beam. And because we're trying to write an equation for the internal actions as a function of where we are in the beam, we need to write a variable that describes that location. So here we're just describing that as the distance from the left-hand end of point A to the position where we've taken our imaginary cut, and we've called that x. Now for this part of the beam to be in equilibrium, which it is, we'll need to have an internal vertical force for some of the vertical forces to be equal to 0. So that of course will be the internal shear force, and we'll also need to have a bending moment to keep the sum of the moments equal to 0. Now before I draw on here my internal actions, I'm going to refer to the positive sign convention for the internal actions. Now if you're watching this video, you'll need to check with your particular textbook and what your lecturer has told you with regards to what is the positive sign convention for internal actions. But for this video, I'm going to use the sign convention as described by the Engineering Mechanics textbook by Hibbler. Okay, so here's the diagram from the Hibbler textbook. So if we look over here, we see our shear force, internal shear action, shown as positive acting downwards on this face. If we were looking at this face over here, positive would be upwards. And for our moments, on this face we have anti-clockwise as positive, and on this face we have clockwise as positive. Okay, so in our example problem, we're looking at this face. So positive shear will be acting downwards, and a positive moment will be anti-clockwise. Okay, so let's draw those in on our diagram over here. So we'll have our shear force, internal shear force acting downwards in the positive direction according to our sign convention, and our internal moment acting anti-clockwise. Right, so now we can write our equations of equilibrium for this free body diagram. So we have start with sum of the forces in the vertical direction to calculate our internal shear force. So we have RAY acting positively upwards, and we have our distributed load acting over this section of the beam, and its equivalent single point load here will be just W times X. So we can put that in. So that's acting in the negative direction, minus W times X. Now just pause at this point here. A common mistake that I see a lot of students make is when they draw this free body diagram here, rather than including the distributed load over this portion of the beam, they'll draw the beam just with this equivalent force here for the entire distributed load, and so they won't have any loading shown on here. So when you draw your free body diagram, you must, when you're taking the cut to work out your internal actions, you must have that uniformly distributed load shown on that section that you're looking at, and then work out its equivalent single point load on that section. So returning to our equation of equilibrium, the only thing we need to include further is our internal shear force acting in the negative direction, all equal to 0. So we can rearrange that to get our equation for the internal shear force as a function of x, which is the position within that section of the beam. Okay, so the next thing to do is to use the moment equation. So what we do is to take moments about the cut end. Okay, so here is the point about which we're taking moments, all equal to 0. So we have RAY times x, and then we'll have our distributed load, W times x, as the equivalent single point load, and it acts halfway along. So that will be just Wx squared on 2, so Wx times x over 2, acting in the anti-clockwise direction about the cut end. And note that we had a negative moment here for the moment effect of RAY because it was going clockwise around the cut end, plus our moment, which is anti-clockwise, all equal to 0, and then we can rearrange that to get our equation for the internal bending moment between points A and B. Okay, so note that this equation that we've calculated here is only valid for the section between the points A and B. So where we've got a change in the loading, okay, that's where this equation is valid until. When we go to draw our shear and bending moment diagrams, we'll want to know the values at important points. So at the start of the beam at point A, so x equals 0, we can substitute that into our equation here, and of course that will be equal to 12. And our moment equation, substitute x equal to 0 in here, and the moment is 0, and we should know that just from the fact that we've got a pin connection here and no moment applied. Alright, so at x equals 4, so at point B, do the same thing again, substitute into our shear force equation. X equals 4 gives us a shear force of minus 20 kilonewtons. Do the same thing for our moment, substitute for 4 into here, and that gives us a moment of minus 16 kilonewton meters. Continuing on with the problem, we're now going to look at section BC. So we'll take our imaginary cut through the section BC. Now we could do what we've done in the previous section, like we did for section AB, and draw our beam from the left, continuing all the way to here. But what I'm going to do instead, to make the equations a little bit simpler for me, is to draw the right hand side. Okay, so we've still taken a cut somewhere through section BC, but instead of drawing all of this side, left hand side here, I'm just going to draw the right hand side of the beam on the right hand side of the cut, and use that to work out my internal actions. Okay, so again, let's put on our load. So in this case, all we've got is our distributed load acting over this portion of the beam. Okay, so now we need to start adding in our internal actions here. But before I do that, let's just go back to the diagram from the Hibbeler textbook, just to remind ourselves of what the positive sign conventions are for our internal actions on this right hand side face. Okay, so our diagram here from Hibbeler shows that when we're looking at the right hand side here, our positive shear force is acting vertically upwards and our positive moment is clockwise. So let's go and put those on our free body diagram. Okay, so starting with the shear force acting upwards as positive and our moment acting clockwise as positive. Because we're wanting to write an equation for these internal actions as a function of where we are in the beam, so where this imaginary cut is, we need to define that So we could define it however we like. We could define x as being from point A to where the cut is and then write our equations accordingly. But what I'm going to do is to define a different variable, call it x dash, and that is from point C, the right hand end of the beam, to our imaginary cut. So this will just make the equations a little bit simpler. Okay, so before we do the equations of equilibrium, we'll just again note that we have the equivalent point load for our distributed load, W times x dash, and it will act at a distance x dash over 2. Okay, so let's start writing our equations of equilibrium. We have sum of the forces in the vertical direction equals 0. So we'll have the shear force, internal shear force V, positive, minus W times x dash. They're the only vertical forces that we have, so all of that's equal to 0. Rearrange the equation and we get V equals 8 times x dash as our shear force equation. Next we take moments about the cut end again, all equal to 0, taking anti-clockwise as positive. We have the moment, internal moment, and note that it's negative because it's going clockwise, and we've defined positive as anti-clockwise in our equations of equilibrium. And then we have minus wx dash squared on 2. Okay, so wx dash times its distance x dash over 2, and it's also going clockwise about the cut end. And that's all equal to 0, so we can rearrange that and get our equation for the bending moment for section BC equals minus 4x dash squared. So again, in preparation for drawing our shear and bending moment diagrams, let's work out some values. So at end C, where x dash equals 0, we can substitute that into our equation. So V is equal to 0, 8 times x dash, which is 0. And our moment is also equal to 0. And then for x dash equals 2 meters, substitute that into here, and we'll get V equals 16 kilonewtons, and substitute it into the moment equation, and we'll get moment equals 16 kilonewton meters also. So 4 times x squared, so 2 squared is 4, 4 times 4 is 16. Now that we have our shear and bending moment equations, we can start to think about drawing the shear and bending moment diagram. So for section A and B, just a reminder of what we had. The equations were shear force equals 12 minus 8x, and the bending moment was 12x minus 4x squared. And for section BC, where we came from the right hand side and we used x dash, we have the shear force equals 8 times x dash, and the bending moment equation was minus 4x dash squared. Okay, so to draw our diagram, let's draw up some axes. On the vertical axis, we have the shear, internal shear force, so we'll do that one first. So at x equals 0, we had the shear force equal to 12, so we can plot that. At x equals 4 at point B, we had the shear force equal to minus 20 kilonewtons, so plot that down there, and we can see that this is an equation in just x to the power 1, so a linear equation, so that will be a straight line between those 2 points. Okay, so now looking at section BC, if we start with x dash equals 2, that gives us the shear force equals 16 kilonewtons, so we plotted that there, and for x dash equals 0, we get V equals 0. Okay, and once again we have a linear equation here, so we should expect a straight line, or we will have a straight line between these 2 points, and that's what we can draw on our shear force diagram. Just note here that we have a step change in the shear force diagram because we have a force here of 36 kilonewtons. So what we should expect to see in our shear force diagram is a step change of 36 kilonewtons. right, which is what we've got here. So minus 20 up to 16 is a step change of 36. Okay, so now let's consider the bending moment equation. So we'll have, again, on our vertical axis, the bending moment in kilonewton meters. And we'll do the same thing again. We'll start by looking at, starting from the left-hand side, x equals 0. And if we substitute that into our bending moment equation, we get, of course, m equals 0. And then at point B, x is equal to 4. If we substitute that into the equation, we get minus 16 kilonewton meters. Okay, so now let's look at section BC, and if we put x dash equals 2 into our bending moment equation here, we get 2 squared is 4, so 4 times 4 is 16, minus 16, so we're at the same point here at point B, the same moment that we got for point B from the equation in section AB, right, which is correct because we have no moment, externally applied moment here, so there should be no step change in the moment diagram. Okay, so now let's put x dash equal to 0 for NC, and of course our bending moment there will be 0. Before we draw the bending moment diagram, let's consider the fact that our bending moment equation here is a quadratic equation, and if we look at the way it's going to go, whether it's going to be a quadratic equation that goes, a parabola that goes like this, or whether it goes down like this, let's have a look at some intermediate values. So let's say we put in x equals 1 into this equation. We would have 12 times 1 is 12, minus 4 times 1 is 4, so that would give us a bending moment of 8, okay, and positive. So we start off by going up, and then we can see that eventually we come down to a negative moment. All right, so if it's a quadratic equation, we can work out where that local maximum is. So let's do that before we actually draw in the bending moment diagram. Okay, so that's our equation. Where is the local max and what's its value? So we know to find the local maximum if we differentiate. So the differential of that equation, where that's equal to 0, will give us the value of the local maximum. Right, so if we do dm dx and our equation here, so differential of 12x is 12, differential of minus 4x squared is minus 8x. So for dm dx to be equal to 0, we of course need x equals 12 on 8, which is 1.5 meters. So our local maximum will be at 1.5 meters from the left-hand end. All right, so let's work out what that value is. So m max local, we just need to substitute our value here that we've just calculated for x into our bending moment equation, and we get a value of 9 kilonewton meters for our maximum, local maximum bending moment. All right, note also that the differential of the bending moment is equal to the shear equation. Okay, so where the shear diagram crosses the horizontal axis, where the shear is equal to 0, that will also indicate to us where the maximum bending moment is. Okay, so now let's put that onto our diagram. So where the shear diagram crosses the horizontal axis is 1.5, where we have our local maximum bending moment, and that value was 9 kilonewton meters. So now we can draw in our bending moment diagram the quadratic parabola for that shape. And then for section BC, again we've got a quadratic equation, and we can plot that in like that. Okay, well that's it. I hope you found that helpful, and I'll see you next time. Thanks for listening. Bye.